This lesson will remind us how we can simplify radical expressions. Notice on these first two problems, the instructions say to find all square roots of each number. A square root is simply asking you what number can you multiply times itself in order to get this answer. When you do not see a square root sign already on a number, and there's just a number given to you with the instruction to find all square roots, remember that there are two. You have to give both the positive and the negative square root, because a positive times a positive will give you a positive number back, but a negative times a negative will also give you that number back. So if I have to identify what numbers I can square to get 625, positive 25 is one of my choices, but I can also square a negative 25, and that will give me a positive 625. Be certain when it says find all square roots, you give both. Now, when you look at 2, it's a fraction, but that's not a problem. We just look at the numerator separately and the denominator separately. What number would you square to get 49? It would have to be 7. That's our numerator. What number would you square to get 144? That would have to be 12. And as a little shortcut, because I have to give both the positive and the negative, instead of writing the fraction twice, if you would like to just put a little plus or minus sign in front of the fraction, that is a perfectly acceptable way to write your answer. Now, another thing that you may be asked to identify with radicals is whether the radical expression would be rational, which means if I were to put that number into my calculator and take a square root, I would either get back a whole number or I would get a number that is a decimal number that would either end or repeat. If it's irrational, when I put it in, I'm going to get back a number that is decimal and it doesn't end and it doesn't repeat. I usually just call it an ugly decimal number, something that doesn't end or doesn't repeat. The third possibility is we might be asked to identify whether it's even a real number, and I'm going to explain what you would look for in order to determine that. So for right now, we've talked about what would make it rational versus what would make it irrational. If you look at number 3, 72 is not a perfect square. So if I put in the square root of 72 in my calculator, I get one of those ugly decimals back. It's a decimal number that doesn't end and it doesn't repeat. That makes it irrational. By the way, when it is written with in radical form, the number under the radical is called the radicand. We want to make sure that we get the vocabulary down that goes with this. So if I mention the radicand, I'm talking about the number that's underneath the radical. Okay, so square root of 72 would be an irrational number. If you look at number 4, here's what the question is asking you. What would be the number that when you multiply it times itself, or you square it, your answer is negative 36? If you see a negative number underneath the radical, and it's an even root, it's a square root, or a fourth root, or a sixth root, that's impossible. There is no way I can multiply a negative number times itself an even number of times and get a negative answer back. If I'm multiplying it times itself an even number of times, I'm going to get a positive. So anytime you have a negative radicand and the index is an even index, a square root or a fourth root, automatically you know it's not a real number. There is no solution for that. Now in number 5, I do have a negative sign, but notice it is outside the radical. All that tells me is they want the negative root. That doesn't impact whether it's rational or irrational. It's possible to find one. I just have to decide if this is going to be rational, irrational, or not a real number. So beneath the radical sign, the radicand is a fraction, 625 over 484. Is 625 a perfect square? The answer is yes. Is 484 a perfect square? The answer is yes. As long as both the numerator and denominator are perfect squares, you have a rational number. If I take the square root of 6,400 that too is going to be rational. If I put it in the calculator, I'm going to come up with something that is not a decimal number that's ugly. It's going to end up being a whole number value. But if you check number 7, because the decimal is where it is, we're taking the square root of 8.1, that creates a problem for me. If the decimal was in front of the 8 or after the 1, this number would be rational, but because of where it is, that makes it irrational. All right, let's review how to use Pythagorean theorem. We have used it in some previous lessons. We remember that Pythagorean theorem is a squared plus b squared equals c squared. And as we read this problem, we remember those steps for solving application problems. If it's something we can draw, we want to draw it. So it says a ladder that's 25 feet long leans against a wall. The foot of the ladder is 7 feet from the base of the wall. How high up the wall does the top of the ladder rest? So what I am expecting is I've got a building, and where it reaches the ground, hopefully they've built it well. It's not like the Leaning Tower of Pisa, and we have a right angle. And then there is a ladder that leans up against this building. Don't worry if your drawing looks to scale or not. Just sketch some sort of right triangle you can use. What I do know is this is the ladder from the ground up the side of the building, and it's 25 feet in length because that's what the problem told me. It also tells me that the foot of the ladder is 7 feet from the base of the wall. So I know this distance has to be 7 feet. What I'm asked to find is how high up the wall the top of the ladder rests. So that's the length or the distance that I want to find. Now, if you remember from before, Pythagorean theorem, the one side I must be careful that I put into the right place in the equation is my hypotenuse. In this case, my hypotenuse is 25 feet. It's always the longest side, the one across from the right angle. So I know the 25 has to go in for the C value. It doesn't matter which of the other two I call A and which I call B. So I would have x squared plus 7 squared is equal to 25 squared. If I simplify that, x squared plus 49 will equal 625. And if I combine like terms, I'm going to have x squared on the left, and that is going to equal 576 on the right. Now, in order to solve this, I'm asking myself, what number do I multiply times itself to get 576? Algebraically, to solve this, what would undo squaring something, the opposite of squaring something, would be to take the square root. So I am putting a square root onto each side of my equation. Now, technically, we need to remember if we're inserting a square root into an equation, there's both a positive and a negative root. However, for this problem, because we're actually looking for the distance that the ladder is reaching up along the building, how high is the distance from the ground, distance has to be a positive value. We don't have to worry about the negative as an option. And if I take the square root of 576, I'm going to come up with 24. So 24 feet would be the height from the top of the ladder down to the ground. Now, if you look at 9 and 10, one thing that's new here is we have these little numbers that are written in the corner of the radical. That is called your index. When we don't see one, we automatically know it's a square root and the index is 2. When you see a number in the corner, it's telling you it's a different root than a square root. For example, number 9 is asking you what's the cubed root or the third root of a negative 64. Now you may have noticed there's a negative under the radical sign. The radicand is negative. If it were an even root, we'd stop right here and say not a real number. But because our index is odd, this is saying what number can you multiply times itself 3 times? And the answer is negative 64. Well, a negative times a negative times a negative will give me a negative answer back. So as long as it's an odd index, I'm going to have a solution. And in order to find it, we're going to do the prime factorization of 64. So 2 goes into 64 32 times. 2 goes into 32 16. 2 goes into 16, 8. And then I'm going to have another 2 and another 2. So because it's a cubed root, in order to simplify this radical, this is saying what can I multiply together 3 times? I'm going to circle up 3 at a time. So if I have 3 of a kind, I circle, here's another 3 of a kind. And out of these groups that I have created, I'll take one number from each group and pull it outside the radical and multiply it together. What you'll notice here is I didn't have anything left behind. I circled up all of my factors. That means this is a perfect cube. So to put it all together, here's what we know. This cube root had to be a negative number, because a negative times a negative times a negative is the only way I'll get a negative number back. And I'm going to have to multiply the 2 from the first group times the 2 from the second group. That means negative 4 is my answer. Now here's how I check to be sure I'm right. Is negative 4 times negative 4 times negative 4 negative 64? If I can multiply that together 3 times and get my radicand, I have simplified it correctly. So negative 4 is the correct answer. If you look at 10, what do you notice? Hopefully you're seeing a negative for your radicand and an even index. Do we even need to do any work? The answer is no. This is not a real number. And that's all you would write. Now we do have a product rule when working with radicals. It simply says that as long as the index is the same, we can multiply together those radicands and write it as a single number. So if I look at the square root of 13 times the square root of 5, that is going to equal the square root of 65. Because 13 was prime, 5 was prime, they had no common factors, there is nothing to try to simplify here, so we are done. If it had ended up being a number that could be simplified, we would want to do that prime factorization and simplify it. If you look at number 12, the square root of 7 times the square root of 7 would equal the square root of 49. But I'm noticing something. 49 is a perfect square. If I take the square root of 49, I get 7. Now, that is a perfectly acceptable way to simplify, but there's another way to think of it. Notice we could have written this as the square root of 7 squared. Well, what happens if you square a square root? They basically cancel each other out. Squaring means multiply times itself. The square root means what can you multiply times itself. When that happens, the answer will always be whatever the radicand is. Notice it's the same thing. Two different ways to think about simplifying, same answer, so they're both correct. Now there's also a quotient rule that goes along with radicals. Depending on the numbers involved, you may find it simpler to think of your radical when it's in fraction form as leaving it as a single fraction underneath one radical. Sometimes it's easier to separate it and take the square root of the numerator over the square root of the denominator. And it really depends on the numbers you're given. If you notice they're perfect squares, you will probably find it easier to separate them. So in the case of 13, where I look at these two numbers, and I know 25 and 81 don't have any common factors, so I can't reduce that fraction down anyway. If I rewrite it as the square root of 25 divided by the square root of 81, that simplifies to be the fraction 5/9. Remember, the radical was already there. It's asking me for the principal or positive root, so all you give is the positive 5/9. If I look at 14, the numerator is not a perfect square, but the denominator is. And they didn't have any common factors, so I simply rewrite it as the square root of 13 over the square root of 121. The square root of 13 does not simplify, but the square root of 121 is 11. And at this point, you have gone as far as you can go. There is nothing more to do. It's simplified. Now, we do have the square root of the numerator over the square root of the denominator in 15. And neither of them are perfect squares, but what I should notice is they have a common factor. In that case, we're probably going to find it easier to simplify if we rewrite it as a single fraction under one radical. So there's other ways to simplify this, but let me show you this way. Remember that even though we don't see it, there is actually a 1 in front of the square root of 24. And we could think of this as the fraction 1/2 times the square root of the fraction 24 over 6. In other words, we could separate it out with taking the numbers that are not under the radical, writing them as a single fraction times whatever the radical is. Now, the advantage in doing this is because 24 divided by 6 reduces down to be the number 4, I have 1/2 times the square root of 4. Now, the square root of 4, that's a perfect square. This is going to simplify so that we won't even have a radical anymore. You may want to put it over 1 so it looks like a fraction times a fraction, and then you would end up with 1/2 times 2 over 1. And then when we multiply this together, we have the fraction 2 over 2, which reduces to the whole number 1. So what did not look like it would clean up to be something nice and neat initially, by applying these quotient and product rules, we can see that it does equal 1. There are other ways to simplify, but this method will certainly work as well. Now, sometimes you will see radicals, and they will have variables with exponents underneath, so we need to know what to do with those. I explained before what we're doing with our numbers is if we take our prime factorization, we would circle up however many the index told us that we would need. So if it was a square root, we'd circle pairs. If it's a cube root, we circle 3 at a time. We can take this, and if we have p squared, that means p times p. Let's just write this out, what it means. Q to the 6th, I'm going to have 1, 2, 3, 4, 5, 6 q's. And since it's a square root, I need to circle 2 at a time. So here's a pair, here's a pair, here's a pair, and here's a pair. Notice I circled everything. Nothing will be left behind. If I take 1 from each group I've circled, I'm going to get p times, I've got 1, 2, 3 sets of q's. So p times q to the 3rd is how this simplifies. Definitely a method you can use. The problem we're going to run into is if our exponents get to be very large, you may not want to write out how many variables it would take if, say, this had been p to the 27th times q to the 81st. So I'm going to show you something you can do that will be a little more efficient when you have variables with exponents. If you look at number 17, we can simplify the square root of 48 the way we already know how. If we were to take the number 48, divide it by 2, 2 will go into 48 24 times, 2 goes 12, 2 goes 6, 2 goes 3. Because it's a square root, I've got a pair of 2's here, a pair of 2's here, and a 3 is left over. So what that means is my 2 times 2 gives me 4 on the outside of the radical, and underneath the radical I will have the 3 that I did not circle. A quick way to check to be sure you've actually simplified correctly, if you put the square root of 48 in your calculator, see what that decimal number is, check to see that it matches when you do 4 times the square root of 3 in the calculator. They should be exactly the same. If they are, you know you simplified correctly. Now, for the variable, rather than write out all of the x's, here's the shortcut you can use. Whatever your index is, in this case it's a 2 because it was a square root, divide it into whatever your exponent is. So in this case we're going to take 2 divided into 7. 2 will go into 7 3 times. 3 times 2 is 6. When I subtract, I get 1 left over. What I now have is this number on top. This number on top is the exponent on the outside, and the number on bottom will be the exponent on the inside. So I'm going to have x to the 3rd power that's on the outside, because this 3 is how many times 2 would go into 7 evenly. x to the first, or just x, stays underneath the radical. And that would be the simplified form of 48x to the 7th. Now, if I'm adding or subtracting radicals, the rule is my radicand and my index have to match exactly. That's the only way they're going to be like radicals. If they don't match, I can't put them together. I have to leave them separate. It's the same principle as in algebra when we work with variables. Remember, if this had been 9x minus 3x, the rule is it has to be exactly the same variable raised to exactly the same power to be like terms, and 9x minus 3x would have equaled 6x. We simply add or subtract the coefficients, and the variable will stay the same. Think of your radicals in the same way that you thought of them when they were variables working in algebra. As long as they match exactly, they have the same index, same radicand, you just simply add or subtract those numbers that are in front, that are like the coefficient. So 9 square roots of 11 minus 3 square roots of 11 is simply 6 times the square root of 11. And that's all you do. If you look at number 19, you have 5 times the cubed root of 10 plus the cubed root of 10. Again, the index is the same. They're both cubed roots. The radicand is the same. Don't forget that in front of that second term, even though we don't see a number, there's really a 1 there. So you have 5 of these cube roots of 10. You're adding 1 more to it. That's going to give you 6 times the cubed root of 10. And if you look at number 20, the issue is you've got the square root of 2 for one radical, the square root of 3 is the other. Your radicands are not the same. That is already in simplified form. You can't do anything else with it. Now, last thing to talk about is how to add or subtract. If you look at the radicands and you say, well, they're not the same, but you notice, wait a minute, these things should be able to simplify. Simplify first, then you can see if you can add or subtract. So, if I were to take 128, which is that first radicand, and I get the prime factorization. Bear with me, it'll take just a moment here. But what you're going to find is, even though this is a little time consuming, you're probably going to see a lot of this work you can reuse. So I'm going to have 1, 2, 3, 4, 5, 6, 7 2's multiplied together to equal 128. Now here's how I'm going to simplify. It's a square root. That means I need 2 at a time. So I'm going to circle up pairs. I have this one left over at the bottom. So if I clean up 4 times the square root of 128, I have my 4 times what's going to come outside the radical is this 2 times 2 times 2 that I have from each of these groups that have been circled. And 2 times 2 times 2 is 8. And then I have this 2 that's left over that stays underneath the radical. Plus, now notice on this next radicand, it's 32. I already have my work starting right here because I divided 2 into 32 and got 16 and so on. If I just look at this point and go down, I have 2 times 2 of 4 that's going to come outside the radical with this 2 on the bottom that stays behind. So I didn't have to duplicate the work. I just needed to go back and pull the part I needed from what I'd already written down. If I simplify, 4 times 8 is 32 square roots of 2, plus 2 times 4 is 8 square roots of 2. Combined, that's going to give you 40 times the square root of 2. So what looked like you would not be able to simplify initially, once it was simplified individually, you then saw you had like terms that you could combine. We can do the same thing on 22. If I were to take 162 and I do my prime factorization, now notice when I get to 81, I'm not using 9 as a factor. I'm going to stick with 3, so I've got the prime factorization because I might need to use it for something else in a little bit. Since it's square roots, I'm still circling pairs. That would mean the 7 that's already outside gets multiplied by 3 times 3 is 9, with this 1, 2 that I didn't circle staying behind underneath the radical. So 7 times 9, square roots of 2, minus 9 times, now there's my 32. I used it over here. Remember, that was 4 that came out. Square root of 2 was left behind. So I've already simplified it once. I don't have to simplify it again. I can reuse my work. This will give me 63 square roots of 2 minus 9 times 4 is 36 square roots of 2. And if I combine those correctly, I should get 27 square roots of 2. The last example we'll look at, we do have some new numbers here we're going to need prime factorization for. If I were to factor 98 into prime factors, 2 goes 49 times. That's going to be a 7 and a 7. So here's a pair of 7s. I'll have 6 times the 7 that comes out, square root of 2, plus, let's factor 72. 2 will go 36 times. 2 goes 18. 2 goes 9, and I get a 3 and a 3. So again, we're doing square roots. That's pairs. So I have a pair of 2s and a pair of 3s. So that means 2 times 3 is 6 comes out. 1 2 is left behind. Now if I do the factorization for 8, I've actually got it right here. That's going to tell me that I get a 2 that comes out and a 2 that stays behind. Now if we clean this up, 42 square roots of 2 plus 12 square roots of 2 minus 14 square roots of 2. When you put all of that together, you get 40 square roots of 2. And that would be your simplified answer. If, for example, one of these had had a square root of 3 in it, we would have 2 terms in our final answer because that square root of 3 couldn't have combined with the other square roots of 2. So it is possible that they won't always all combine, but many times you will find after you simplify they will.